Yes. Tamanna, now you can start.
Yes, sir. Good morning, everyone. Myself, Sreda Tamanna, the state coordinator of Microbiome Society India. And today I welcome you all here in the invited lecture series. And I'm very happy that with us we have A.M. Desmukh, sir, the All India President of Microbiome Society India, along with all the eminent members. Before introducing to the guest lecture of today, I would like to welcome you all and be comfortable uh, with all the technical issues. So, in today's lecture, we have with us Mr. Ajay Kumar Soni, who is the Associate Vice President of Prague Metrics R&D Center, a unit of Prague Industries Limited, Pune. So, Mr. Azhar had over 30 years experience in technology management and driving the first generation ethanol fermentation process development program at Pragnatris. He is a MSc in microbiology from Shivaji University, Kolhapur, and presently pursuing his MTech, integrated MTech PhD from Savitribai Phule, Pune University. He also had a membership of boards of studies with Shivaji University and earlier worked as a SAF East Corporation, Ciplam, and in Citric India Limited. So he had traveled across the world for eternal fermentation, commissioning, and problem solving. We're very pleased and glad to have him with us today and to enrich our knowledge regarding food waste valorization. So now I'd like to request Ajay sir to share his slide and to carry on with today's lecture series. And also I would like to request all the participants to kindly cooperate and be ready with your questions and doubts if any. So Ajay sir, you can continue.
Thank you, Tamanna, and thank you for giving my introduction. Also, I would like to add one more thing. I am student of Dr. Arvind Deshmukh. He is my teacher. He was my teacher, and still he is my teacher because we interact regularly and share our thoughts and our knowledges. I thank you for Microbiology Society of India for arranging and giving me opportunity to share my thoughts. Now let me share my slide, and I will start. And anyone has any doubt, he can stop me in between. I would like to not to start my video, and I request other also not to start their video because it may interfere in our communications. Is the slide is visible?
Yes, sir, it is visible.
Yes,
Okay.
yes, video.
Yeah. Now in focus, I would like to give some things totally which are related to microbiology. My initial slides, they are related to fermentation related matters, food waste. And at the last, also I want to share few things regarding our company, my department, my Matrix R&D Center, and a small corporate presentation of my company. So we will start with the fermentation product, which are normally fermented products are available, and since decade they are being manufactured fermentation by fermentation. Various feedstocks used in fermentation. So the molasses, grain, and such kind of things. Then we will go to food waste. How food waste can become an ideal feedstock for fermentation. Its composition and its potential components as nutrients for fermentation. Schematic diagram of pretreatment. Food waste directly cannot be used as a feedstock because It has no uniformity, and it contains so many different components in terms of sugars, carbohydrates, proteins, fats, minerals, vitamins. Everything is present there, and it is not identical throughout the season and throughout the places. I have taken one example of ethanol fermentation because presently I am working on ethanol fermentation, how food waste can be utilized ideally as a feedstock for ethanol fermentation. I have done some calculation how the process can become commercially viable. Pre-treatment things, so that also we will cover in this presentation, and parameters for commercial viability. It is not that just food waste can be taken and fermented. Some things which are needed for consideration. Now you see the slide, there is two pictures. One is food waste and another is fermentation medium. So food waste just is available. We have collected it from municipal solid waste department, and then we have, just we have grinded it and converted into, see how it looks. It looks like it's just fermentation medium. Just my slide is not getting down, just give me some time. Okay. So typically, if we check the municipal solid waste, because it contains so many things, the sample has collected from Pune Municipal Corporation Solid Waste Department. If you see and divide it into various components, the biodegradable solids, if you classify 1,000 kg or 1 ton municipal solid waste, there is biodegradable solid waste is around 450 kg and non-biodegradable 550 kg. Out of that, kitchen waste is 200 kg and non-kitchen solid waste. So the difference between kitchen waste and non-kitchen waste is, kitchen waste is just from domestic kitchen collected from various houses, restaurants and hotels. We have here in Pune a system that every day morning a vehicle for collecting such kind of waste comes, and they collect and take it to treatment plant. The non-kitchen solid waste is a kind of plant drops, leaves, branches, then vegetable market, or such kind of uncooked material. Uncooked biological material that is considered as non-kitchen solid waste. So from kitchen waste, we have tried and done fermentation. We see that from 200 kg kitchen waste, we can get ethanol by fermentation and then distillation 9 to 11 liter. So if we see 1 ton of municipal solid waste after segregation of various products, we can get 9 to 11 liter of ethanol. And if you non-kitchen solid waste, if you carry out biodegradation or biomethanation, we can get around 14 to 16 kg of CNG. So this CNG directly is a purified methane gas, which is directly used as a fuel and can be used as motor fuel. Non-biodegradable waste, we know that some things are organic or inert waste, which can be recycled or used for landfilling. So we are not going to talk of this. Now we see various fermentation products. Here in, not only in India, but all over the world, we know that ethanol can be used as fuel, biogas can be used as fuel, isobutanol, nowadays, Praj is working on this, and isobutanol having higher calorific value and is relatively non-inflammable. It can be used as fuel, And in few years, probably you will hear that isobutanol has replaced ethanol. It will take some time, but at the moment, Praj is working on this, and we are getting some good results. Probably before few months, fuel, which is isobutanol fuel, is used in aircraft. In addition to ethanol, now isobutanol can be used as fuel in aircraft. Lactic acid, polylactic acid, bioplastic, these are the need of the day, need of the world, as they are born to replace plastic, which is considered as one of the potent pollution.
रंजन कब से लगता कैलेंडर वो पुराना है क्या?
Pardon me?
है ना?
Okay. Citric acid can be used by fermentation. Sorbitol, sweetener, these are confectioning, is used in confectionaries in chewing gum. Antibiotics, we know that from years together is used and produced by fermentation. Dairy products are cheese and these things are used as
वो
a
secondary है, वो हमको नहीं मालूम. Now we are dealing with Kakare. Kakare is coming and talking me to understand he is the main person. His property. So हम उनसे बात करेंगे.
Somebody's voice is there. Please stop the. Some noise is there.
He's not on the call.
Some noise is there. Please stop the.
पहला से उनकी मंडल के लिए देगा, फिर मंडल वाले उसके आ
Hello.
जाएंगे. हम मंडल को
Are you able to hear me?
पीछे क्या हो रहा है उनको मैं क्या बोलता हूँ.
Are you able to hear me? Are you able to hear me?
Yes, sir, we can.
So please, someone has asked them to stop the mic. So various feedstock. For ethanol, we know molasses, grain, tubers, cellulosic material. Commercially, these feedstock being used for ethanol. For biogas, we know distillery spent wash, agri waste, municipal solid waste. For isobutanol, we use molasses, grain, lactic acid, molasses, grain, tubers, citric acid, sorbitol, antibiotics, dairy products. These are various feedstock used conventionally because they have given their commercial, commercial suitability for manufacturing these fermentation products. But now the time has come to look towards some non-conventional feedstock, and we are looking as a food waste, as a non-conventional feedstock for manufacturing such these products. These are some samples of foodstock while we did the experiments at our matrix. We collected some feed material. This is a restaurant waste, food waste from Aund, Katras, Bolero, Yerola. These are various areas from which we collected. Now the food waste processing, we took the food waste from these various locations, and then we grinded it into, without adding any water, we could get such kind of material which has various important nutrients. Now we all know this is a processed food. So for hotels and restaurants, they use oil for cooking. And before conducting any kind of fermentation run, we need to remove the oil. This is for de-oiling, we need hexane or other solvents are used so that oil can be separated out and the remaining material can be used as fermentation medium. Now, if you see, these are various samples which are very important for all of us to know. The solids, they are in the range of 20 to around 19, 20, 21% solids, and rest around 80% is water. So we know that if we have this so much water in any food material, it is bound to get spoiled. Already due to its nature, highly perishable nature, it can get easily contaminated by various organisms. The fats are around 5%. If you see, the fat can be removed, separated out by solvent, and can be used in manufacturing of biodiesel, which is being done since long time in Western countries. The proteins you can see around 2%, 3% there proteins are there. The most important thing, the starch. If you see the 3%, 7%, 6% starch material is there, phosphates are there, and another thing is bacterial count. If you see the bacterial count varies much, around 10 to power 7 to 10 to power 9. So this count varies due to its how much time you have kept it idle, how much time it has taken for transportation. So due to this reason, the bacterial count varies. And carbohydrate. The carbohydrates, they are glucan, arabinol, and in turns, we call this as a cellulosic material. If you see, these are around 1% to 2%, 0.5%. It also varies a lot. And these are some free sugars around glucose, maltose, sucrose, then fructose. They are free sugars because we know that the food material, it contains some fruit material also. So if you see starch, cellulose, and free sugar. So collectively, if you see the concentration of this carbon source is around 6 to 7% or 8%. So if you compare this with molasses or grain, so after dilution, for example, if molasses has around 40% fermentable sugar, so to make it fermentable, we have to dilute around 3 times. So the resultant fermentable sugar concentration in molasses come to around 10 to 12%. And here it is around 6 to 7% or 8%. So this is little bit closer to the fermentation medium. So before taking this directly to fermentation, we need to do some kind of pretreatment. So why we call this as a potential feedstock? Because it contains carbohydrates, proteins, fats, vitamins, mineral, and water. The important thing here, we need to consider the water. Because in any fermentation industry, the water is required to dilute the feedstock. And here, water itself is ready. So we can imagine that for the fermentation industry, external use of water can be minimized because water itself is coming from feedstock or food waste. Anyone are you able to hear me?
Yes, sir.
Okay. So if anyone has a question in between, so he can ask me, or if you feel at the end also you can ask me. Now you see the important slide. Why microorganisms produce ethanol or citric acid or vitamins or lactic acid? Why they produce? They do not produce this fermentation product because mankind requires it. These products are done, or they produce this because they are a part of their life cycle or their pathway. These are the for microorganisms, fermentation products, they are byproducts. While producing these products, they get the energy in form of ATP. So microorganisms, they want ATP, and for getting ATP, for getting energy, for multiplication, for their own life cycle, for growing their own numbers, they require this carbons, nitrogen, phosphorus, and such kind of things. So they require the carbon, oxygen, nitrogen. For example, if you see around 50% of cellulose is carbon. These are some important things I did not have to discuss in detail because you probably can go through this slide later. So the important thing here I want to mention is that these products, microorganisms required for its own growth, and these products or these elements or these sources can be provided by food waste. A small things where actually in our laboratory we did the experiment where we did 5 kg kitchen waste batches were taken, oil was separated, some kind of physiochemical pre-treatment, for example, particle size reduction. Then enzymatic treatments. Now we know that this food waste contains free sugars, glucose, fructose, sucrose, which doesn't require any kind of pre-treatment because they directly can be consumed by yeast. Starch is present. Starch cannot be consumed by microorganisms, especially by yeast, Saccharomyces yeast. And for its conversion to fermentable form, it requires enzymatic treatment in form of liquefying enzyme or saccharifying enzyme and saccharifying enzyme. Then they have cellulose. Cellulose also cannot be directly broken down in the form of xylose and glucose. It requires cellulolytic enzymes. So such kind of pretreatment is done, which we call it as the enzymatic pretreatments. And after performing these treatments, we used active dry yeast, which was available in market, and initial concentration was kept to 150 to 160 million cells per ml. And for fermentation was carried out at 32 degrees for around 30 hours. And we had so many batches, around 5 repetitions were there. These are laboratory fermenters where we use, this is the setup of our laboratory. Here you can see this. Here we conducted the fermentation batches. And at the end, at the end of 30 hours, we got 7 to 8% volume by volume ethanol concentration. So 7 to 8% volume by volume ethanol concentration indirectly says that the fermentation medium had the sugar concentration around 13%. So from 12% or from 8% sugar concentration in food waste, we have to concentrate to some extent, and then we can get this so much alcohol concentration. So if you calculate the yield of the food waste, this was concentrated food waste, and where the solid material in the term, when we say pre-treatment we did for removal of some suspended particles also. Those suspended particles were removed by means of filtration, and the left fermentable free-flowing medium was used for fermentation. The yield was around 48 to 52 liters per metric ton of this concentrated food waste. So this is comparable with the molasses. The molasses, C-grade molasses, if you see, having around 35 to 40% fermentable sugar, it has the yield of around 230 liters of ethanol per ton of C molasses. Here we are getting 48 to 52 liters per metric ton. So this is the free medium where we are getting relatively good amount of ethanol. Now this is a small calculation where I will just go through this fast. So after in Pune city, we are getting around 325 tons of food waste per day. This calculation has been done before a couple of years. So at the moment, we are getting around 400 metric ton. After pre-treatment and concentration, we get around 178 metric ton of syrup, fermentable syrup, having sugar concentration 13% and solids 32 to 35%. So if you see, by this pre-treatment, we get the sugar around 234 metric ton and having sugar extraction efficiency around 80%. This is not bad. This is quite good efficiency. So some costing. The overall pre-treatment requires pre-treatment. I am not considering here the steam required for ethanol distillation. The pre-treatment cost only for converting food waste into syrup. The cost is around you can see that 1,08,000 kind of thing. The total enzyme cost, this price is also here. Then cost of electricity. So if you see the transportation, grinding, all it transportation is considered in next slide. But if you see the overall cost of electricity and everything is considered, oil separation cost of biodiesel produced. At the last, if you see the total cost for sugar extraction is around 6.81 Indian rupees per kg of extracted sugar, which is equivalent to 10 US cent. At the moment, it is at the time of this, it was around 70 rupees dollar. Now it is 80 rupees. So there will be some difference. But 6.8 rupees per kg of sugar, what is for us to know now. So if you see, sorry, if you see the costing of 1 kg of one metric ton of food waste. Now this is for 1 metric ton. Costing is around, if you see, 88,960 rupees, which considers the extra treatment cost, transportation cost, and all other variable costs, considering we get around 88,960 rupees per metric ton of food sugar. Now, if you see the conventional feedstock, where directly we get the molasses price is around 60,000 rupees per ton. This price to some extent varies. In sugar extract or sugar mill, when it is operative, the cost is around 4 rupees a kg or 4,000 rupees a ton. And when there is no sugar mill in operation, the price goes to around 8,000 or 9,000 rupees a ton. So this is variable. But in all, if you compare the total equivalent by keeping all identical conditions, the price of food waste is around 88,960 rupees, and to get same quantity of sugar, we require 96,000 rupees of 96,000 rupees if you get the molasses. So you can see, despite having so much transportation, then processing, ultimately we save some amount of money. So in future, this can become a potential feedstock. When there is scarcity of molasses, grain, cellulosic material, food waste can be considered as the best alternative feedstock. Pardon me? Okay. So now in addition, sometimes if you need some, apart from ethanol fermentation, if you want to do some other kind of fermentation, we can add few other nutrients. Now, for example, here we have added some sugar cane syrup we have added, so that we can see the material consistency of material become like this. We can do fortification, because some fastidious organisms, they require some additional nutrients in terms of vitamins, cofactor. So those can be added, and the food waste can be, in addition to ethanol, that can be used for other products, other fermentation products. Further, it can be dried, and which can be made easily transportable. This is food waste after treatment and extraction, everything finally dried, so that can be bagged and transported to fermentation plant. This is a typical schematic flow diagram. Here, if you see the grinder, then here it is a de-oiling is done in this part. Then enzymatic treatment, some kind of pre-treatment where particle site reduction, further reduction of particle site, then addition of some chemicals which are required for pre-treatment, enzymatic treatment, some treatment for cellulosic enzyme, then amylolactic enzymes. That kind of treatments for different vessels are required. And finally, these are evaporators, where we can get a concentrated food waste, which can be used or stored, or can be used or can be transported. So ultimately, for any sugar, any fermentation industry, if you need to consider food waste as a feedstock, segregation is the most important thing, because we know that all over India or anywhere in the world, food waste can be doesn't come as is. people have tendency to mix with other inert material, plastics, and this, the segregation is important thing. The transportation, time required for transportation. We know that food waste is perishable material, and transportation takes longer time, then food waste gets spoiled, and it adds into the treatment cost. So timely pre-treatment, food waste has reached its site, but it is lying or dumped because it smells, it stinks. So we need to do it timely treatment. Distance between collection center and treatment plant. Now, this is again a very important point. We have villages, towns, cities, where everywhere we get the food waste. So if we imagine or consider a plant which can get at least a small distillery can be made, where at least we can have 350 to 500 metric ton of food waste, and can be converted into distillery having around 20 to 30,000 liters per day ethanol plant, which can be used as a fuel. Finally, treatment costs, the cost of enzyme, cost of steam, cost of electricity, everything has to be considered. And fortification cost, if you need to add vitamins, if you need to add some additional sugar and some other grain powder or grain flour can be used here. So by addition of all such kind of thing, we can get a fully furnished feedstock. Now, this is the final end of my slide for food waste to ethanol. This is an excellent way to eliminate nuisance happening worldwide. Everywhere world is, you know that treatment is making nuisance. Food waste is available in each village, town, city, world. Project can establish a chain of industries to produce fermentation feedstocks. Now, this is again is a very important point. For food waste processing plant, you need not have to have your own distillery. Just this can become a small scale industry also. Any microbiologist, anyone who has just come out from the graduation, post-graduation, he can set up the plant. He can has a chain of people who can collect the food waste from different part of the city. He can have the small kind of grinder. Then he can have small tanks, vessels, and finally he can end up with, or he can have at the end, a food feedstock having a defined sugar concentration, proteins, and whatever required concentration is required, he can maintain it there, and he can become a supplier of a different fermentation industry. For example, if I have a citric acid plant and I want a feedstock with a particular composition, so that I did not have to buy it from sugar factory, I did not have to buy it from grain. I will buy it from a person who has a food waste treatment plant. So it will be cheaper for me to have a food waste converted into feed rather than taking directly molasses or grain. So such kind of plants can supply a different kind of food waste, food feed to different kind of fermentation industry. This become a small scale industry worldwide. This will also give us the employment generation at organized, non-organized, and technical sectors. Technical sectors are we as a microbiologist. Organized sectors, we the employers or employment, and then non-organized sector means the people who can go to houses, who can go to hotels and restaurant in the morning with a small 2, 4, 5 tankers, where they can collect this food waste. So this for collection of this, education is not required. So food waste industry can become a kind of future industrial sector, I would like to say, and right consumption of food waste. And it will not be, I will not exaggerate saying that after 5 years or after 10 years, people will come to your place, your house, to buy the food waste. Now food waste has become the problem, but after some time people will come to your house to buy the food waste. So this change is, and we should wait for, we as a microbiologist should wait, and we will see that the time will be there. Certainly there will be this time. So thank you for this, your attention. Now I will welcome if you have some questions on this, so that after this, I will have one more small presentation that will give us the idea of my company, our R&D center. So the questions are welcome.
Sir, this is Dr. Shikhar Gaikwad from MIT WPU. A very nice presentation and very nice information you have shared, sir.
Yeah, thank you so
one
much.
basic question, yes, sir. One basic question is there from my side. So when you are saying that you are collecting food waste and for removing the oil, you are doing centrifugation. So that step is enough, or some more chemical treatment is required to remove oil from the food waste, sir?
At plant scale, at laboratory scale, we can use hexane. But at plant scale, it is possible we can use hexane. A typical kind of centrifuges are available at commercial scale. They are called as tricanter. Where we use decanter, and for removal of oil, tricanter is used, where to food waste, grinded food waste, the hexane is added, and it is passed through tricanter, where hexane along with oil comes out, and food waste, this grind food waste separated out. So this hexane can be further evaporated and recycled back to food waste, and the oil which is separated out from hexane can be used in making biodiesel. And this process is being done since so many years in United States to make biodiesel.
Okay. So one more question, sir. So the oil which we are segregating, are we using the same oil in the process of fermentation or in generation of bioethanol, or we are treating that oil as a waste?
No, this oil is not treated as a waste, nor it is taken into fermentation. It is used for making biodiesel.
Okay. Fine. But you said, sir, you are using food waste for producing bioethanol.
Yes.
And the oil which you are removing, that too you are using for in generation of bioethanol?
No, it is biodiesel, not bioethanol.
Okay, sir. Okay.
Biodiesel is separate, different, and bioethanol is different. Bioethanol is produced by fermentation, and
Yes.
biodiesel is produced by esterification of oil, cooked oil, separated out from food waste.
Okay. So how you are how you are defining the quality of oil, and on that basis you are using it for the generation of biodiesel, sir?
See, for biodiesel, or it is esterification chemical process.
Okay.
And it has its own composition. So if we go through the biodiesel making from vegetable cooked oil, we can get so many papers and so many procedure in web or in net. It is established since so many years. It has been established to get the biodiesel from vegetable cooked oil. It is vegetable waste oil, you can say.
Yes.
Waste oil.
No,
So,
my question is, sir, when we are using a particular oil for cooking, so and it is a waste, so it is having a combination of oils. So
yes.
The quality is also going to affect when we are talking about the generation of biodiesel, sir?
No, that quality will not affect biodiesel formation. See, the biodiesel, producing biodiesel requires fatty material, or it requires any oil.
Okay.
Any oil means you can, waste oil can be used, food waste oil can be used. Then if you see, there are many plants commercially working on this.
Okay.
There are some other non-edible oils. They are in market and they are being used for making biodiesel.
Okay. Thank you so much for clearing my doubts, sir. Thank you so much.
Thank you. Any other question?
Hello, sir.
Yeah.
Good morning, sir. Myself, Dr. Bharat.
Yeah. Yeah, Mr.
Sir,
Bharat, tell me.
actually food waste contain lot of, when we are taking from that food waste from the municipal solid waste, that is the source, yes. So in that case, this food waste contaminated with the so many bacteria, so much of fungi. So how shall we eliminate those bacteria and fungi during this process?
Correct. See, municipal solid waste, I have done the classification, the municipal are nowadays all over the world, degradable, you may be knowing that wet waste and dry waste are being collected everywhere in the world separately. So if you see the chart, just give me a moment, I will show you the chart. Sorry, my slide is not getting.
Okay, sir. I remember that first slide.
Yeah, you remember that. So
yes, sir.
So though the chart is here, this is just for the sake of our understanding. These two parts, biodegradable solid waste and non-biodegradable waste, they are not collected together, they are collected separately. And from this biodegradable solid waste, kitchen waste is also collected separately. What your point is also correct, that it has microorganisms, and you have seen that in my slides also I have shown the from 10 to power 7 to 10 to power 9 microorganisms are present per gram
Yes,
of
sir.
waste. So we cannot eliminate it, but we have to, while processing, we have to heat. There is a heat treatment. Now, for example, when you do enzymatic treatment, the temperature required is around 90 degrees. For 90 degrees, we have to heat for 3 hours. So during this part, this can be the microorganisms almost get eliminated or dead. Some spores are present, but the spores, before getting time to germinate, we have to pass it to fermentation and take it out of fermentation and distillation. So this is not a sterile treatment, or this is not a sterile process where microorganisms have to be eliminated totally. Microorganisms, presence of this is semi-sterile process. Presence of microorganism cannot eliminate or cannot be eliminated, but we have to do the process with little bit hygienic conditions so that their presence will not eliminate, or they would not minimize our yields. And for doing some special fermentations, for example, citric acid fermentation or lactic acid fermentation, sterilization is required so that these microorganisms can be totally, have to be eliminated totally.
Okay, sir. So, sir, if in case if you go for the sterilization, again there is a, in this food waste we have a lot of sugar cells. Again, is it possibility to go that product going to as a char? Yes, sometimes it's possible. So is it okay for the sterilization at 120 degrees centigrade for at 15 lbs pressure? Is it okay?
Yeah, it is okay. It is being done. For example, there are separate special kind of plate heat exchangers where the fermentable material is diluted and it is passed to plate heat exchanger, where temperature goes to 120 degree. It is flash. For a few seconds, the temperature reaches to 120 degree and immediately is further passed to the further part of heat exchanger where further it is cooled. So it is possible.
Okay, sir. Sir, one more last question, sir. Sir, in generally food waste, generally it is pH is very low, 3 and or 4 pH. Actually, I worked with the food waste for some time, so I observed this phenomena. So it is immediately it is pH is getting down. So how are you rectifying this issue in your experiments?
Yeah, for food waste after treatment, the pH goes lower than 4. For ethanol fermentation, pH 3.5 to 4 pH can be okay. You do not have to add caustic.
Okay.
So what happens in such condition? Little bit reaction may get prolonged, but it is okay. We have to minimize the chemical consumption.
Okay, sir. Thank you, sir. Thank you very much.
Thank you. So if no question now, I will just pass go for my another presentation, very small presentation.
Yes, yes, you can proceed.
Yeah.
There are few questions in chat box. Tamanna, you can ask later on.
Yes, after the presentation, we'll discuss regarding this.
Okay. And I request others to mute your mic, mute your audio. Yes, Ajay, you
Yeah, I'm
can
sharing.
share the slide.
Is the slide is visible?
Yes, yes.
Yeah. Okay. So come back. This is our R&D center, and this has almost completed around 15 years. And this is, if you see, this is in our company, Praj Industries Limited, is best place worldwide. It is best place to work. It's the first number worldwide. Then we are in biofuel industry. We are number 2 in world, and in 50 industries. And consecutively for next year, again we are number 3 in biofuel industry worldwide. So we have this is first of its kind R&D, where bench scale, pilot scale, and commercial scale trials are conducted at the same place. Here, so the technologies that we develop for ethanol fermentation, lactic acid fermentation, isobutanol fermentation, biogas, biomethanation, CBG, and 2,3-butanol, many processes already we have developed. So all the processes they pass through this lab scale, pilot scale, bench scale, and then commercial scale. We have 76 plus technologists, and as you know, Praj is known for green technologies. So we add to society, to country, and we work mainly on sustainability. We have continuous design and development, D&D, not only R&D, but D&D, to improve our water footprints and energy footprints. Nowadays, we know that energy consumption and water consumption has become a real criteria for success of any industry. So we simultaneously work on that. We develop renewable chemicals along with biofuels and advanced biological tools or biotechnology tools we do. We are certification by DSIR Government of India, and we have around $30 million investment from our own, and we have some other foreign investors also, like Vinod Khosla, who was the co-founder of Sun Microsystems, and he was the shareholder of Praj. See, we have around 20 PhDs and 56 masters. All they are in microbiology, biotechnology, analytical chemist. We have some center of excellence. So analytical science, scale-up and process engineering, bioprocess technology, molecular and microbiology, and chemical sciences. For analytical sciences, we have very high-tech laboratory instruments for chromatography, GC, HPLC, ion chromatography, then spectrophotometry, UV visible, FTIR, ICP, sulfur analyzer. Composite properties, we have rheometer, warm calorimeter. These are mainly used for chemical technology. And fuel properties, viscometers or flash point. These are mainly required when we have to use different kind of fuel. So we have bioprocess technology expertise where applied microbiology, molecular biology expertise is there. Fermentation having various microorganisms. So we have our own microorganism bank, and we have around 200 to 300 microorganisms consisting yeast, bacteria, fungi, and algae, for producing various biochemicals. We have expertise in process modeling and simulation also. Enzyme application of processing feedstock, various kind of enzymes for starch, cellulose, downstream processing. So this also we have the expertise. It is not that we do fermentation, estimate only, and then stop the work. It is not that. We further, at the end of fermentation, we take the feedstock or we take the fermented mash, further carry out purification, passing through various ion exchange regimes and various kind of distillation apparatus. Also, we have to separate out the product of interest. Heat and energy integration with effluent management and expertise. We have our own separate division for effluent management also. So microbial genetic modification expertise, although I am not much versatile to these techniques, but we have just to mention molecular yeast typing, yeast breeding. We are experts for molecular yeast typing, yeast breeding, reverse engineering, metabolic engineering, and bioprospecting. So we are in bioeconomy that leveraging FTP, the biomobility. Biomobility is the CBG, bioethanol, isobutanol, and from these using these technologies for renewable chemicals, materials, and for this the impact on environment, economy, and social job creation. All these things are there. I just not going to read this because the time has coming to complete finish. So the renewable chemicals we have from sugar, we have cosmetics, so hyaluronic acid, we have technologies for this. Then fish oil and vegetable oils, where we can have nutraceutical, pharma and cosmetic application. From lignin, we can have oil in infrastructure, biobitumen. So if you see this 1 star, 2 star, and 3 star. So wherever you see 1 star, they are ready for commercialization. These PLA and PHA, these are for at bench scale at the moment. And the other technologies where you see the biobitumen, this is at pilot scale. So all these technologies commercialized, under commercialization, and some are at different stages of development. So with this, I finish my presentation. And thank you so much for giving attention to my presentation.